All right, welcome everyone. Look, if you've ever felt completely bogged down by the math of acid-base equilibria, well, you're absolutely in the right place. Today, we're going to demystify this whole chemical landscape. In this explainer, we'll be equipping you with a literal roadmap to help you navigate any solution with absolute clarity.
So to really understand this map, we've got to understand the terrain itself first. And that all starts with water. I mean, why is water the ultimate chemical chameleon? Well, it actually has this crazy dual identity. Even in totally pure water, there's this fascinating process going on called self-ionization. Basically, two H2O molecules will bump into each other and actually break apart, forming a perfect balance of a hydronium ion, that's H3O+, and a hydroxide ion, OH-. Water is constantly acting as both an acid and a base to itself, which sets the baseline for everything else we're about to explore.
Okay, let's dive into this. Here is our itinerary for today's explainer. First, the power of hydrogen. Then, the acid-base roadmap. Third, the magic of buffers. Fourth, reading titration curves. And finally, measuring pH in reality.
All right, part 1, the power of hydrogen. Or, as I like to call it, water's secret identity.
So our primary coordinate system here is pH. Now, because hydronium ion concentrations vary over, massive orders of magnitude, we use the negative logarithm. Why? Well, it just generates a positive, super easy to read scale for us. This is what gives us the standard pH scale, right? Where pure water at 25 degrees Celsius sits right at a perfectly balanced neutral 7.
Just to ground ourselves before we go further, we're relying on the Bronsted-Lowry definitions here. Basically, an acid is a donor of hydrogen ions and a base is an acceptor. It's really that simple. Introduce an acid, it donates H+ ions, lowering the pH. On the flip side, introducing a base gives those H+ ions an acceptor, shifting the balance the other way and raising the pH.
Moving right along to Section 2, the acid-base roadmap. Time to navigate the terrain.
Okay, so here is the crucial point. Think of this as the golden rule for solving these problems. It is always a two-step dance. Step 1, limiting reagent stoichiometry. Basically, when you mix things together, you first pretend they react 100%. Just completely ignore equilibrium for a second. Let the strong players entirely consume whatever they can. Then, and only after the dust settles, do you move to step 2. That's re-equilibration, where the leftover chemicals settle into their final comfortable balance. Master this two-step process, and honestly, you've mastered the map.
Now this map is divided into 4 distinct territories, or regimes. Regime 1 is the pure solution. That's where you just have your starting acid or base. Regime 2 is partially neutralized, meaning you've added an opposing chemical, but hey, not quite enough to wipe out the original one entirely. Then there's Regime 3, exactly neutralized. They match perfectly here, leading to what we call hydrolysis. And finally, Regime 4 is excess, where you've just completely overrun the original chemical with your added acid or base. Just keep in mind, the landscape looks very different depending on whether you start with a strong acid, like hydrochloric acid, which breaks apart completely, or a weak one, like acetic acid, which only partially breaks apart.
On to Section 3, the magic of buffers, holding the line. This is where things get really cool. When you have a mixture of a weak acid and its conjugate base, they actually act together like an invisible shield. If you add a strong acid invader, the conjugate base just absorbs it. Throw in a strong base invader, the weak acid neutralizes it. The result is almost magical. The pH of the solution barely even flinches. It completely prevents those massive chaotic pH spikes from happening.
And yeah, there's absolutely a mathematical spell behind this magic, known as the Henderson-Hasselbalch equation. It elegantly calculates the pH of a buffer by taking the pKa, which is just a constant specific to the acid, and adding the logarithm of the ratio between the conjugate base and the weak acid. Basically, as long as that ratio holds steady, your buffer holds the line. It's a massive shortcut for chemists, for sure.
All right, Section 4, reading titration curves. Let's visualize the map.
Now this visually brilliantly illustrates the difference between our weak and strong acids. Notice that bottom blue line representing a strong acid, hydrochloric acid. It starts incredibly low on the pH scale, stays relatively flat, and then boom! It suddenly shoots up a steep cliff when neutralized. But compare that to the top red line, our weak acetic acid. You see a gentle upward slope there. That slope is the buffer region, actively resisting the change, right up until it finally reaches its own smaller cliff.
The terrain gets even more beautiful, honestly, when we look at polyprotic acids. These are acids that can donate more than one proton. Think about the carbonic acid in your blood or in a soda. Notice those stunning overlapping waves? As the pH changes across the bottom axis, the dominant form of the acid smoothly shifts. It trades away one proton, cresting that middle wave, and then trades away a second, cresting the right wave. It's pretty amazing, but buffer systems in biology use these exact waves to perfectly tune the pH of our bodies.
And finally, Section 5, Measuring pH in Reality, the tools of the explorer.
So let's move to the physical world. One of our most colorful tools in the lab is the pH indicator. Indicators are actually weak acids or bases themselves, but they have this really special property. When hydrogen ions attach or detach from the indicator molecule, the molecule physically changes its shape, and that structural change alters how it absorbs light, giving us a literal visual color cue. Litmus goes from red to blue, phenolphthalein flashes from totally colorless to a brilliant pink, and bromothiamyl blue shifts from yellow to blue. Each indicator basically operates in its own specific pH window, telling us exactly which part of the map we're on.
But, when we need exact precision, we turn to high-tech tools like this pH electrode. Instead of color, this device uses electricity. It relies on something called the Nernst equation to track the activity of hydrogen ions with pinpoint accuracy, measuring the voltage difference between the inside of the probe and your sample. Honestly, it's like a highly sensitive GPS for our acid-base map.
Now, what's really interesting about this is that you can have the best map and the most expensive equipment in the world, but if you ignore temperature, you are going to get lost. As the Measurement Handbook points out, temperature is literally the most common cause of error. Why? Well, because the self-ionization of water itself shifts when heat is applied. If the temperature changes, a solution's pH will literally change, even if absolutely nothing else was added to it. Which leads us to a fascinating final thought for this explainer. If that equilibrium shifts with heat, is a neutral pH always exactly 7? Think about it. The answer is actually no. At higher temperatures, pure water produces more ions, and its pH drops below 7. Yet, it remains perfectly neutral, because the acids and bases are still equally balanced. It's just a brilliant reminder that the landscape of chemistry isn't just some static piece of paper, right? It's a dynamic, breathing world. The map is always shifting based on the environment, just waiting for curious explorers to chart it. Definitely keep that in mind next time you step into the lab.